It's hard to stop instantly without overshooting. But when most of us program our wheels or lifts to move to a certain position and then stop, that's exactly what we're doing. One way to control your robot's movement more precisely is called PID control.
PID stands for Proportional Integral Derivative.
The proportional part is easy to understand. All it means is that the closer we get to our destination, the less power we exert. Programming this with motors isn't too hard.
We're going to run this process in a continuous loop and set our desired value to some encoder reading, let's say 2000. We're going to call the number we read from the encoder our current value and define the error as the difference between the two. Let's also assign the error to another variable called p-value to make it clear that this is all related to the proportional part of our PID controller. Sometimes a proportional controller is all you need, but there are times that require a bit more sophisticated method. Let's say we're trying to set an arm to a target position. The arm starts out far from its target position and the motor power is correspondingly high because it's proportional to this error. This motor power pushes the arm closer to its target, which reduces the error and therefore reduces the motor power. However, unless the target position is completely stable, the arm can never reach it, because if it did, the motor power would become zero and the arm would drop. Instead, with proportional control, the arm will stabilize at a value that's slightly offset from the target. This offset is known as droop. We can mitigate the effects of droop by increasing the constant of proportionality. However, making the motor too responsive can lead to oscillations in the arm position. Having your lift oscillate is, well, bad. To solve this issue, we use integral control. To our initial expression, we add a new term that's proportional to the integral of the error over time. In other words, the integral term takes into account accumulated error over time, making it impossible for the arm to settle at any value other than the target. To approximate accumulated error in Robot C, we add the current error to a running tally, which we started at 0. However, weighting the integral term too highly can cause the position to overshoot its target value as it seeks to compensate for past error. Now for the derivative. We add another term that responds to the rate of change of the error. To counteract the tendency of the proportional and integral terms to cause the value to overshoot the target, the derivative term takes into account the rate of change of error, slowing down the motor if the position is reaching the target at too high of a rate. To implement this in code, we simply take the difference between the current error and previous error. Now we perform a weighted sum of each of the three PID terms. Each one needs a constant of proportionality. For now, we'll pick these values arbitrarily, but they're important and they need to be tuned precisely. The proportionality term should be your most important factor. Too high of a weight, however, will lead to oscillation, whereas too low of a weight will increase droop and the time needed to stabilize. The integral term usually has the next highest weight. Its effects are similar to those of the proportional term. The derivative term, on the other hand, leads to a smoother, more gradual stabilization process when its weight is increased. Here's what it looks like when we put it all together. PID control can be used pretty much any time you need to set a system precisely to some target state. It can be tricky to implement, but the benefits are often well worth the trouble.